All right, so let's get started. So chapter 2 is actually kind of a long chapter. We're going to break it up over the next 2 weeks here. It's got these two disparate topics that they kind of cram together. The first one revolves around what are called electron pushing arrows, and that's what we're going to discuss today. This will be sort of a brand new concept in organic chemistry that we use to help talk about chemical reactions. And then there's also the acid-base portion of the chapter as well, which we'll cover next week. All right, so first of all, just to kind of take a step back, as we said, a big focus of organic chemistry is focusing on chemical reactions. All right, and so how should we be thinking about chemical reactions? Chemical reactions are these processes that make and break chemical bonds. Or since we're in organic chemistry and we know that we're restricted to the non-metals on our periodic table, we can be even more specific. What types of bonds are we talking about in this course? Covalent bonds. All right, and importantly, what are those covalent bonds made of? All right, when we talk about a covalent bond, it is a shared pair of what? Electrons, right? So importantly, these bonds that we're making and breaking in chemical reactions, these are made of electrons. And so that's really what's happening in a chemical reaction is you're shuffling around electrons. You're changing which atoms are bonded together by shuffling around those electrons. All right, and so that's great. We can talk about a chemical reaction looking at a balanced chemical equation. Or we can look at an extra special piece of information, what's called a reaction mechanism. All right, this is, again, more information than just what your reactants and products are. All right, so a reaction mechanism, this is a step-by-step details of how a chemical reaction occurs. Okay, this is how a chemical reaction occurs at the molecular level. So a reaction mechanism, kind of just simply put, is what you would see if you were to hop into your magic school bus and shrink on down to the molecular level and actually watch this reaction taking place, right? The exact kind of step-by-step breakdown of what is going on in that chemical reaction, okay? It's composed of a series of what are called elementary steps. So breaking that reaction up into what are called elementary steps, the exact details of that reaction, as well as you'll see any intermediates. That may be formed. Okay, intermediates. These are molecules that are produced and consumed in a reaction. So they don't ever appear in your balanced chemical equation. They're produced in, say, step 1 and then consumed again in step 2, right? So they never actually appear in your overall chemical reaction. Reaction mechanisms, this bit here, you actually would have discussed in Chem 1B in the kinetics chapter. Remember we said that you can't figure out the kinetics of a chemical reaction just by looking at the balanced chemical equation, but if you had this extra special piece of information, the reaction mechanism, then you actually could figure out what the kinetics of that reaction were, right? If you had all those details of exactly how that reaction was going down. That was that fast, slow step business, right? How the kinetics were always dependent on the slow step in your reaction mechanism. Okay, cool. So same idea, we're talking about this same concept here. In organic chemistry, we're going to add one other detail to these reaction mechanisms that's going to be very important. Our reaction mechanisms here are going to show the motion of electrons, right? The movement of those electrons throughout the course of that chemical reaction. All right, using what we call electron pushing arrows. Okay, so again, importantly, the title of today's lecture was that electron pushing arrows. What do electron pushing arrows do for us? They show the motion of electrons throughout the course of a chemical reaction, right? Again, what's happening in a chemical reaction? We're making and breaking bonds. Those bonds are made up of electrons. So if we can show how the electrons are moving around, we can show how exactly that reaction is occurring. All right? Cool. So we're going to do this, like I said, next week is a big focus on acid-base reactions. Acid-base reactions is something you touch a little bit on in Chem 1A. You talk a little bit more in depth about it in Chem 1B. We're going to go even more in depth about it in organic chemistry. So that's a good kind of example reaction to start with here, since it's something that's at least a little bit familiar. So let's get a balanced chemical equation. We're going to take hydroxide, and we're going to combine it with HCl. And I want everybody to take a second and reach back in your brain to Chem 1B, where you learned how to predict the products of this reaction, of these acid-base reactions. See if you can't tell me what the product should be of this reaction. Does anybody know what one of them is? Give me one of them. So we got water, and what's the other one? That chloride ion, yep. Cool, so remember an acid is a proton donor, so that HCl loses that hydrogen. The base is a proton acceptor, it accepts that hydrogen, and that's how we get water and chloride. All right, so to be clear, what we just drew here is what we would call a balanced chemical equation. Tells you what your products are, tells you what your reactants are, but there's not much more information about how this reaction is actually going down. So now what we're going to do is we're going to draw the reaction mechanism. Okay, we're going to pick this because it turns out to be a relatively simple, just one-step mechanism. But again, we're going to be showing the movement of electrons. In order to do that, we can't just use our chemical formulas. We need to go to our actual structures of our molecules. So we're going to do our Lewis structure for our hydroxide ion. In our formula, it's OH with a -1 charge. But looking at our Lewis structure here, we can actually say, where does that negative charge live? On which one of those atoms? On that oxygen atom. That negative charge is the formal charge on oxygen. All right, we got our HCl. Our chloride ion likes to have 1 bond and 3 lone pairs. We got our water. Okay, and if I have the chloride ion with its -1 formal charge, how many lone pairs is it going to have? Can't have 3, we can't break our octet rule. Our halogens, they like to have one bond and 3 lone pairs. This is chlorine with its formal charge of 0. If I'm going to give it a formal charge of -1, I've got to turn this bond into a lone pair, increase the amount of electron density on there. So our halide ions, chloride, fluoride, bromide, that is when that atom has all 4 lone pairs, or rather all of its octet in terms of lone pairs. Okay, cool. So now we need to put in these electron pushing arrows. But before we do that, we're just going to take a step back and look carefully at these structures and play the spot the difference game. Right? What bonds do we see that are broken in this reaction? And what new bonds do we see are formed in this reaction? So we're going to color our broken bonds in orange, and the new bonds that are formed in green. Anybody see a bond that gets broken in this reaction? The HCl bond. All right. What new bond do I get formed in this reaction? My OH bond in my water. Okay. So we have a bond broken and a bond formed. Again, that's the basis of any chemical reaction, making and breaking bonds. All right. But now what we want to do is think of like, well, where did those electrons go? I said that that HCl bond was broken, right? Where did those electrons go? They didn't just disappear into thin air. So now we want to pay careful attention not just to the bonds, but also the lone pairs. Do we have any, rather, do we lose any lone pairs? Or do we gain any new lone pairs? Which one do we lose? For my hydroxide. So oxygen on the left-hand side has 3 lone pairs. On the right-hand side, it just has 2. All right. What do we gain any new lone pairs in this reaction? On our chloride ion, right? Chlorine has 3 on the left-hand side. It has 4 lone pairs on the right-hand side. All right. So importantly, where did this pair of electrons go when we broke that HCl bond? They had to go somewhere. What happened is it was converted into a lone pair. So this extra pair of electrons on that chloride ion, those didn't just appear out of thin air. They used to belong in that HCl bond. So this pair of electrons that we colored in orange on the left, that bonding pair, is the same pair of electrons that's over here on the right. It's just now it's a lone pair. All right. Likewise, where do we think that pair of electrons that was on my oxide ion went, my hydroxide ion went? They're now my new bond over here between oxygen and hydrogen. Right? So this pair of electrons over here is the same. Okay? And that's exactly what our electron pushing arrows are going to show. All right, so for right now, I'm just gonna draw these in, and then we'll worry about like the rules for these arrows and worry about drawing them ourselves and all that sort of jazz. But right now, we're just gonna get an example of what these look like down, okay? So we got our new bonds that are broken and formed here. All right, if I'm gonna show the formation of this new bond, I'm gonna draw an arrow from my lone pair over to that hydrogen atom. Right? This is my new bond that's being formed between those two. Okay, what our electron pushing arrows, what you kind of want to imagine is wherever the base of that arrow is, you're taking that pair of electrons and dragging them over to a new atom. So in this case, I'm dragging that lone pair over to that hydrogen atom, creating that new bond. All right, likewise, I'm going to show this bond breaking. It used to be between hydrogen and chloride. Now it's just sitting on that chloride ion. So I'm going to show from that bond over to that chlorine. Okay, this is my bond breaking over here. All All right, so these are our electron pushing arrows. Again, they show the details of this reaction, the movement of electrons as that new bond is being formed and as that old bond is being broken throughout the course of this acid-base reaction. In this case, there's just one step, right? One sort of jump from our reactants to our products. This is a fairly simple mechanism. They could be 3 steps, they could be 20 steps, right? It depends on just how complicated that reaction is. Okay, so this would be our mechanism. We have our balanced chemical equation for our acid-base reaction, and then we have the full mechanism down here actually showing the movement of electrons throughout the course of this reaction. That's what a mechanism is doing for us. Extra special piece of information. Okay, let me just say that at this point, we have not studied any reactions in this course, right? We know a little bit about acid-base reactions from last semester, but again, we're going to recover acid-base reactions. So I'm going to put down a bunch of different reactions that you've never seen before. You're not supposed to be like, ah, yes, I know that reaction. No, no, no. Everything's going to be brand new to you today. The whole point is you're going to trust me that these reactions actually do happen, and you're going to focus on making sure that you understand these arrows that I'm putting down, being able to follow them as well as being able to read them and draw them in by the end of the class. Okay, so don't worry about the reactions themselves. Basically, throughout the course of this semester, what we'll do is we'll learn a new functional group, we'll learn some reactions, and a few of those reactions will even go as far as to learn the mechanism for, right? And again, that's that extra special piece of information that you could know. The most you could know, the holy grail of information about a chemical reaction is its mechanism. Okay, but we're not even there yet. So, right, basically the old goal of today is to be able to follow these arrows and draw them in. That's the ideal. Okay, cool. All right, so first of all, let's talk about rules for our electron pushing arrows. Okay, so first of all, important to keep in mind, these show the movement of electrons not atoms. All right, so when you're drawing in these arrows, you're showing what's happening with the electrons in that chemical reaction. Because of that, electrons are negatively charged, right? So if we're moving around electrons, we have to be very careful to watch for changes in formal charge. Those bonding patterns that we discussed last class period or last week are going to be really important in this discussion of electron pushing arrows because we need to make sure that we're keeping track of our formal charges. All right, one big trick that we're going to use that's going to help us out is we want to make sure that we conserve the net charge of our reaction. So basically, if we look above, we started out with a net charge of -1 in our first step. We better also have a net charge of -1 in that second step as well. There's a conservation of that net charge. So keeping that in mind will help you make sure that you're bookkeeping your charges correctly. Charges are like a notoriously difficult thing to keep track of. Okay, so we talked about bonding patterns. That's one little trick. We also want to keep in mind about this conservation of net charge. Our net charge will be the same at every step in our mechanism. It's got to be. All right, and then the most important 2 rules for when you're drawing in your arrows. The base of the arrow has to be at a pair of electrons. That can either be a bond or a lone pair, but it has to be at a pair of electrons. All right, let's just convince ourselves of that in our previous example here. Our first arrow, the base of that arrow is at the lone pair on that oxygen. Our second arrow, the base of that arrow is on that bonding pair of electrons, right? But the base of the arrow always lives on a pair of electrons. Okay, and then the head of the arrow. This is on the atom, points to an atom. And that atom is accepting that pair of electrons. All right, so again, going back to our previous example here, the head of my arrow was at this hydrogen atom. It was accepting that pair of electrons, forming our new oxygen-hydrogen bond. All right, in our other example here, the head of that arrow was on that chlorine atom. That chlorine atom was accepting that pair of electrons, becoming the chloride ion. All right, so base of the arrow at a pair of electrons, head of the arrow at an atom. Okay, and there are certain patterns that we're going to see over and over again for our electron pushing arrows. All right, the first is bond breaking. Okay, if we look up above, when we broke that bond, our bonding pair of electrons became a lone pair. All right, and that's going to be a common theme we're going to see over and over again when bonds break. Bonding electrons become lone pairs. Or we could have bond formation. All right, in our previous example, when we formed that new bond, it was the exact opposite. We had a lone pair becoming a bonding pair. All right, and I'm going to leave room for one more here. We got one more to add, but we're going to stick with these two to start out with. Okay? Cool. All right, so step one in this whole learning how to use these electron pushing arrows, we're going to first focus on following our electron pushing arrows. Meaning I'm going to put them down and you're going to try to draw me what the product would be of that step. Okay, and let me just say what you want to try to do is first look at that electron pushing arrow and categorize it as being either a bond breaking arrow or a bond formation arrow. Okay? Whichever one of those two categories it's going to fall into, that's going to help you better understand how to draw your product. All right, so step one. Everybody take a second and see if you can't give me the product of this step in a mechanism. All right, what do we have? Bond breaking or bond formation? So this is starting at a bonding pair of electrons, right? That moving that bonding pair of electrons onto that chloride or onto that chlorine. So this would be a bond breaking arrow. So that bonding pair of electrons is going to become a lone pair. So let me draw my two products here. All right. I broke that bond. I took that pair of electrons that was that carbon-chlorine bond, and I turned it into a lone pair on that chloride ion. What am I missing here? Charge. So my chloride ion, as we discussed, has to have that negative formal charge, right? 4 lone pairs, that's a negative formal charge for a halogen. But I got a problem here. My conservation, right? If I look, everything's neutral over here on the left-hand side. That means everything has to add up to be neutral over here on the right-hand side. So if I have a negative charge, what else must I have on there? A positive charge. All right, so where does that positive charge go? Well, again, if we think about our bonding patterns, over here on the left, my carbon in the middle had 1, 2, 3, 4 bonds. Over here on the right, it's only got 1, 2, 3 bonds, which means it has that formal charge of +1, right? Or a carbocation. Okay, and what happened is that carbon was chilling all happy with its complete octet, and chlorine stole that pair of electrons from it and turned it into a lone pair. All right, carbocation's probably the hardest to spy in terms of formal charges because we have implied hydrogens a lot. So it's not exactly clear just by drawing this, which again is why that conservation of net charge business is so important. All right, let's do another one. I'm going to start out with a carbocation here. Okay. Got this negatively charged ion here, this sulfide ion, and we're going to draw an electron pushing arrow from that lone pair on that sulfur over to our carbocation. Everybody's going to take a second and draw me the product of this. Remember, first you want to categorize it as a bond breaking or a bond formation arrow. All right, which one, breaking or formation? So this would be forming a new bond here. I'm starting at a lone pair. So this would be a bond formation. And specifically, which two atoms am I forming a new bond between? My carbon and what other one? My sulfur, all right? Some people like to attach these things backwards. Importantly, it's my carbon and my sulfur that are going to have that new bond. All right, it's the lone pair on that sulfur that's forming that new bond. This lone pair right here. is going to make up my new carbon-carbon bond. So everybody take a second, draw me my product, and then I want you to double check your answer by counting carbons. All right, we should have the same total number of carbons over here as we have over here. Don't accidentally add one or take one away. All right, I got my 4 original, and now I'm going to draw my new carbon-sulfur bond. All right, and my sulfur had these other 2 carbons on there as well. So I'm going to add those on there. So I picked up this lone pair of electrons on that sulfur and I dragged it over here to form a new bond with this carbon atom. So again, this pair of electrons here becomes this bonding pair of electrons in my new molecule. I got my 1, 2, 3, 4, 1, 2, 3, 4 original carbons plus these 1, 2. So again, counting carbons is a good extra little double check to make sure that you didn't actually introduce or take something away. All right, let's do another one. Again, we're just trying to follow these arrows. Okay. This is actually another acid-base reaction, but using organic acids and organic bases. All right, so now we got 2 arrows going on here. Let's look at this first one. What is this one doing for me? Bond breaking or bond formation? So this will be a new bond here. So this one's a formation arrow. And what about this one over here? Bond breaking or bond formation? This one would be a bond breaking arrow. All right, so we'll draw our first product here. We have our nitrogen, but what used to be a lone pair on that nitrogen is now a new nitrogen-hydrogen bond. All right, likewise over here, what used to be this bonding pair of electrons is now going to be a lone pair on what atom? on my oxygen. All right, and what am I missing? Charges. So where's one of them? The oxygen's got its 3 lone pairs. That means it's got a -1 formal charge. Something's else got to be missing one too, though, right? Because everything was neutral up here. So I better have a sum up to be neutral down here. My nitrogen. My nitrogen's now got 4 bonds and no lone pairs, meaning it's got that positive formal charge. Yeah, that's fine. I wanted to show that bond explicitly just so I could show where this pair of electrons went. But yeah, you could do NH3 with the plus. Got to have the plus. All right. So again, that was an acid-based one. Let's do another one. I'm actually going to put 2 down here. That are a little bit more complicated than what we've done before. All right, so I'm going to put down 2 different examples and give you all a few minutes to work through. All right, so while y'all are working, I'm going to quietly kind of fill in the answer up here so you can double check your work. All right, so focusing on this first one here, we have this bond formation arrow, my lone pair forming a new bond with the carbon. And at the same time, we kick off this bromine, we break that bond there. So we have this pair of electrons going from being a bonding pair to a lone pair. And then on my other one, my bond formation, my lone pair becomes that bonding pair of electrons between oxygen and carbon. All right. For this one down here, this bond formation arrow is pretty straightforward. We're starting out with the lone pair ending at this carbon atom. But what type of arrow would this one be here? Breaking or formation? So it's starting at a bond, right? And we're dragging it over to that oxygen. Importantly, though, we're only going to break one of these two bonds in this carbon-oxygen double bond. So we'll still have one. Now my oxygen has an additional lone pair. So it's got that negative charge. And now we have a new carbon-carbon bond with my nitrogen at the end. Okay, that lone pair on that carbon has now formed my new carbon-carbon bond over here. All right, so looking at our electron pushing arrows, we want to first be able to categorize them and then sort of follow them by drawing what the product of those steps in our mechanism are. Now we're going to move on to trying to draw them ourselves. All right, and what we're going to do is we're going to take a look at a mechanism for a reaction that we'll study later on down the road. Here's the chemical equation. If we take an alcohol, mix it with hydrochloric acid, we will get a what we call dehydration reaction, where we lose water and the OH is replaced with a chlorine. Whoops. All right, I'll put in my lone pairs. Here's my chemical equation. But now we're going to show the reaction mechanism. All right, so I'm going to put down like the before and after, and I want you to try to draw in the electron pushing arrows that will accomplish that step. All right, so in the first step in our mechanism, we're going to protonate that oxygen. So you're going to draw in the electron pushing arrows that will accomplish this first step in our mechanism. What bonds need to be formed? What bonds need to be broken? Do we need to break any bonds? What bonds do we need to break? The HCl bond, right? So in order to break this bond, I'm going to start with my arrow at that bond, and I'm going to drag that pair of electrons over to that chlorine, forming my chloride ion. So here's a bond that we broke, turning that bonding pair into a lone pair. Do we need to form any new bonds? Which one? Oxygen to hydrogen. Yeah, we always got to start at a lone pair. So this will be my bond formation arrow, turning this lone pair into that bonding pair. All right, I'm not done yet. This mechanism has multiple steps. I haven't gotten to my products yet. All right, so the next step in this mechanism, we get our same chloride ion. But now we also have water and a carbocation. All right, figure out what bonds are being broken, what new bonds are being formed. That will help you draw in those arrows. All right, and once you get that, the very last step, you can fill in again, electron pushing arrows. Well, let's just break it up. Do we have any new bonds being formed? No, I don't have any new bonds being formed. Do I have any bonds being broken? So I'll just need one arrow in here. All right, a bond breaking arrow, which means we're going to start at that bond we're trying to break. Drag that pair of electrons over onto the atom that's accepting that pair of electrons. So in this case, I'm breaking my carbon-oxygen bond and giving that pair of electrons to that water molecule. All right, so just one arrow for that next step in our mechanism. And then the last step here will form our product. And we got that water molecule floating around still. All right, so now we need to fill in the arrows on this last box here in our mechanism, or rather the third box on our mechanism, to finish it off and get us to our products over here. All right, what new bonds are being formed? What bonds are being broken? Yep. Do we have any bonds being broken? No bonds being broken. Do we have any new bonds being formed between our carbon and our chlorine, right? So I'm going to start out with that lone pair on that chlorine and drag that pair of electrons over to form that new bond with what was my carbocation. Okay? So again, above is what we would just call our chemical equation. Down below, this is where we showed the step-by-step details of exactly how that reaction was going down. All right. Again, you wouldn't know this off the top of your head. You just kind of trusted me at each step of the way here, but we were able to fill in those arrows to jump from one step to the next. And this is kind of a good example. Sometimes we'll learn reactions, and all we'll really learn are the chemical equations, like what products are created. But other ones we'll do a deep dive into, and we'll actually learn the mechanism as well, and that'll teach us something about that chemical reaction. This one goes through this carbocation intermediate, which has certain consequences and blah, blah, blah. So we'll learn about, that's kind of a preview as to where we're going to be going throughout the course of this course. We're going to do one more of these. Let's just jump to our mechanism here for the sake of time. Whoops. All right, so again, you're going to put in the arrows that would take us from step 1 to step 2 in this reaction. Are we breaking any bonds? What are we breaking? Yeah, we're breaking one of those two carbon-oxygen bonds. Are we forming any new bonds? Which one? My oxygen and carbon bond over here is being formed. So where did that bonding pair of electrons come from? Well, it was this lone pair over here on my hydroxide ion. So I'm going to draw an arrow from that lone pair to that carbon that it's bound to. Likewise, I'm going to show this bond breaking, and where did that orange pair of electrons go? Became a lone pair on that oxygen there. All right. So then the last step here, again, you're going to fill in the missing electron, pushing arrows up here on our intermediate structure. Oops. Oh no, that's not what I want. All right, so after the last step in this mechanism, we'll have a chloride ion and a new carboxylic acid. All right, do I need to break any bonds? My carbon-chlorine bond needs to get broken. And am I going to make any new bonds? Yeah, my double bond, my pi bond here between the oxygen and my carbon. Where did that pair of electrons from that new bond come from? They were up here on my oxide ion, comes down, forms that new bond. Right? Likewise, where did that pair of electrons go when I broke that carbon-chlorine bond? They became this lone pair on that chloride ion. So I'm going to show that bond breaking and that pair of electrons jumping onto that chloride. All right, so we have our bond formation of our carbon-oxygen double bond and then our bond breaking of our carbon-chlorine. And this would be the mechanism of this reaction here. Cool. All right, so we said that there were patterns of our electron pushing arrows, bond breaking, and bond formation. I told you there was going to be one more that we add here. This is when we do a bond breaking and formation all in one shot. All right, what we're going to see is our bonding pair of electrons becomes another bonding pair. All right, and we're going to see this in sort of a specific context. What are called alkenes, meaning they have a carbon-carbon double bond, or an alkyne, which is a carbon-carbon triple bond. Okay, so this is when you have like a higher order carbon bond, you see these bond breaking and formation arrows. All right. So let's take a look at an example. All right, we have this carbon-carbon double bond here. If we react this with, let's say, HBr, okay, we're going to get one normal one that we saw before. We're going to have our normal old bond breaking arrow here. But my other arrow here is going to break this carbon-carbon double bond and form a new carbon-hydrogen bond. All right, so this one here is going to break the carbon-carbon bond and form a new carbon-hydrogen bond, all in one shot. All right, so real quick, everybody just look up this pair of electrons right here that's in my carbon-carbon double bond. It's going to swing around and form a new bond with that between carbon and hydrogen. So it's going to get stolen away from this carbon atom over here. All right, so let's draw our product. So first of all, one of my products is that bromide ion. All right, let's draw our next product. Should have how many carbons? Those 4 that I started out with. We've broken that carbon-carbon double bond, so I'm not going to draw that. All right. I want to make a point here. So I'm going to go and I'm going to fill in what are our implied hydrogens in this molecule here. All right. We have 3 on the ends. These actually don't matter, but I'll fill them in just to be good. How many hydrogens are on each of those interior carbons? Just 1, right? Because they have that carbon-carbon double bond and then a single bond, so each one of these only has 1. When I go over here to my products, all right, I'm going to put those existing hydrogens on there, and then I'm going to draw a new one in for my new carbon-hydrogen bond that's been formed. Right? To be clear, this pair of electrons here that was my carbon-carbon double bond now makes up this new carbon-hydrogen bond. All right? I'm not done yet, though. What's missing? Always a pain in the butt with mechanisms. Charges, all right? So if we look carefully here, everything was neutral over here, so everything better be neutral over here. I know I have a negatively charged bromide ion, so what am I missing? That positively charged carbocation. And that's why I filled in those hydrogens explicitly, so we can see this carbon over here only has 3 bonds. So that means it has to have that positive formal charge. That purple pair of electrons got stolen away from that carbon atom. It was all happy on the left-hand side with its complete octet. The hydrogen came along and stole that pair of electrons away from it, so now it's left with that positive charge. All right, and if we want to be good and just finish this mechanism here, this is just a normal old bond formation arrow, so everybody take a second and add that on there. All right, it's a little busy with those hydrogens on there, which is, again, why we like our bond line structure. It makes it a little bit less busy, but nonetheless, I just need that bond formation arrow from my bromine to my carbocation, forming that new carbon-bromine bond. All right, and we're just going to note here that we formed a carbocation. Important intermediate step here in our mechanism. All right, and then the last one that we want to sort of have under this same category, bond breaking information, is kind of the reverse of what we saw here. All right, so this hydroxide is going to come and steal this hydrogen. That's going to cause this pair of electrons to come down and interact with this carbon and kick off that halogen all in one shot. All right, before we move on, I want you to label these three arrows. I'm going to give you a hint. We got one of each here of our patterns. One of them is a bond breaking arrow, one of them is a bond formation arrow, and one of them is doing both breaking a bond and forming a new bond all in one. All right, let's call these arrows A, B, and C. Which one's my bond breaking arrow? A, B, or C? C. So this one will be breaking that carbon-iodine bond. Which one's my bond formation arrow? A, B? A. This one's my formation arrow. All right. So importantly, B here is we're both breaking a bond. Which bond are we breaking? Between which two atoms? The hydrogen and carbon bond is going to break. And what bond are we forming in this same step? A carbon-carbon bond. Awesome. All right. So my products here are water, that iodide ion. And now we have this new carbon-carbon bond. There was already one of them there. So that means this second one here is going to be a carbon-carbon double bond that's formed. All right, this pair of electrons here has now reached down to form this new carbon-carbon bond. All right, and these alkenes will be one of the first functional groups that we really study, at least in terms of reactions. So this sort of type of pattern here will be important at the beginning. But again, it's going to be something that you see when you either create a carbon-carbon double bond or you're using one of those alkenes as your reactant. You get this bond-breaking formation pattern all in one arrow. All right, cool. So we got our electron pushing arrows. We got to make sure that we follow our rules for drawing our arrows. The base of the arrow is always at an electron pair, whether it's a bonding pair or a lone pair. And the head of the arrow is always at an atom accepting that electron pair. And there's three patterns that we'll see over and over again. Bond breaking, where a bonding pair becomes a lone pair. Bond formation, when a lone pair becomes a bonding pair. Or we can have both breaking and formation in one. These are going to be unique to compounds that have carbon-carbon double or carbon-carbon triple bonds. And these are where our bonding pairs of electrons become other bonding pairs of electrons. Cool. All right.